Hello and welcome back. In this video we'll be discussing section 5.1, jointly distributed random variables, the discrete case. So 5.1 considers both discrete and continuous random variables. This video will be only over the discrete. So to begin with, let capital X and capital Y be two discrete random variables on a sample space S. So they're both defined on the same sample space. Then the joint probability mass function, or joint PMF, not PDF, it's PMF, probability mass function, for x and y is given as follows. So it's denoted by little p still, but it has two inputs, little x and little y. And this is defined in the following way. It is the probability that capital X takes on the value little x and capital Y takes on the value little y. So this and could again be thought of as an intersection. And a common way to write this is just the probability capital X equals little x, comma, capital Y equals little y. In other words, both conditions must be met. And so how can we imagine this? Is that we have our sample space S, which is just our collection of outcomes to some experiment. Now, how a random variable is defined is it's a function. So in this case, we'll let y look as follows. So it's a function that takes inputs that are outcomes from the sample space and outputs that are real numbers. So for this, to draw just a picture, I'm going to say capital Y only takes on three values. So these 3 points here. And let's denote them by dashes actually, not points. But on the same sample space, we have another random variable x. And let's, for just simplicity, suppose x, capital X only takes on these 4 values. Then it follows that these grid of points drawn here are all the possibilities that we can get from capital X and capital Y as a result of plugging in some element from the sample space or some outcome. So remember to just kind of remind ourselves of random variables. The idea to think about S, these may not, capital S here might not be numbers at all. They could be things, they could be people. What they are is that they're outcomes to some experiment. And yes, capital X and capital Y are functions on the sample space giving back numbers, but a way to think of these is that these random variables is that they're measurements. So you give some element or outcome from your sample space, you get back measurements of that outcome. So for example, for a sample space with a set of people, in a previous example, we talked about heights of people. So maybe capital X still refers to heights of people. But instead of just recording the heights of people, maybe we record the heights and the weights of people, which would then give the following picture. So with joint PDF, the joint distribution, is we're talking about the distribution of two random variables. And it has this sort of picture. So for example, if we were to actually give values, such as, let's say it goes 1, 2, 3. This is a rather simple example. Then this point that I've underlined here corresponds to the point 4, 3. Okay. And P, evaluated at this point, represents the probability that capital Y takes on the value 3 and capital X takes on the value 4. So what are some properties of this joint PMF? It will be the same two properties as before. One is our joint PMF is non-negative for all ordered pairs X and Y that are possibilities for capital X and capital Y. So sit in the range of capital X, capital Y. If we sum up all the different ordered pairs, so P of X comma Y, sums up over all possible ordered pairs. This is also written more standardly as a double sum. So you sum up over all the X values and sum up over all the Y values of the following must add up to a 1. And this makes sense because if these are all, if we add up the probability at each one of the points for X and Y, then the sample space is distributed over these points. So if we add up the probabilities at each one of these points, it should add up to 1, just like before. So to be a little more precise, we can let capital D be the set of possible values of the ordered pair of random variables x comma y. And so this can be seen to be sitting inside the plane, so inside of R2. Then for any subset A that sits in D, the probability that our ordered pair of random variables takes on a value that's an element of A can be seen to be the sum over all the possible values in A and the probabilities at each one of those points. So how can we see this visually? It looks like the following. If we make our grid again, let's reproduce it. And let's this, what I've put as the dotted line around these 6 points, be our set A, which is contained in D. And what is D in this case? D is the set of points I comma j such that I is greater than or equal to 1, less than or equal to 4. And j sits in between 1 and 3. Again, I and j are integer values, where I falls between 1 and 4, and j falls between 1 and 3. Both of these inclusive, meaning that it can be the endpoints. And so the probability that capital X comma Y is an element of our set A here will be expressed as the following double sum. Well, in this case, if we look at what's circled from 3 to 4. And these circle points are also all the points y that run from 1 to 3. So many times, even though that this is written as a single sum, such an expression can be expressed in terms of a double sum, which we'll see is computationally beneficial in many places. So marginal probability, or the marginal probability mass function, is defined as follows. So the marginal probability mass function of x, or more simply, the PMF of x, is given by, so it's still little p of x, but we put a subscript capital X here to indicate that this is the probability mass function of the random variable x, because now there's more than one random variable. There's two. There's x and y, capital X and capital Y. So by definition, this is the probability that capital X takes on a value little x here. Looks like this. It's the sum of our joint PMF, summed up over all possible values of y with x fixed. So this might look like an expression or a function of two random variables, of two inputs, x and y, two variables, but that is not true. This is only a function of little x, because y here can be thought of as a dummy variable or an index. So after we sum up over all the possible values of y, our results will only be an expression of x. So similarly, these look like capital P's, but I assure you they're little p's. So little p sub capital Y of little y is the probability that capital Y takes on the value of little y, and the roles are just reversed. It's the sum over all possible values of x of little p of x comma y. So to see this, that this is actually true, I make the following argument. So we can notice the following. So p sub capital X of little x is the probability that capital X is equal to little x. This can be thought of as the probability that capital X is equal to little x and capital Y is equal to little y1. We'll call it little y1. Or capital X is equal to little x and capital Y is equal to little y2. And it goes on for all the possible values that capital Y can take on. So we are breaking the case of x is equal to little x into these disjoint cases. Now, since each one of these events are disjoint, we can use our rule of probability. So these ORs are again just unions. So by our rules of probability, it's the probability of the first event. In other words, capital X equals X and capital Y equals little y1. So on and so forth. So adding up all these disjoint cases. So in closed form, this is just the sum over all possible values little y of the probability that capital X is equal to little x and capital Y takes on that value little y. So this is discrete, so this is a sum where we're adding up over these discrete values, so a sequence of values that capital Y can take on. But by definition, this is just little p evaluated at the point little x comma y. So we can see that we're getting precisely as the statement above. So using these things, so marginal probability, so the marginal probability mass functions and the joint probability mass function, we'd like to do an example. So let x and y be discrete random variables with the following joint PMF. So our PMF is given by the following. At each of the pair, at each x and y, it's defined as follows. And this is for only integers x comma y falling between 1 and 3. And it's 0 elsewhere. So what is the value of k? So that's our first question. So this will be three parts, A, B, and C. So the first thing is, what is the value of k? So we're going to use our definition of a PMF, joint PMF, in order to answer this question. So if we sum up over the possible values of x and y, this should be equal to 1, since this is in fact a PMF. So joint PMF here is given as follows. Well, it's 0 everywhere besides where x and y are the integers from 1 to 3. So this reduces down to the sum. X is equal to 1 to 3. Y is equal to 1 to 3. Of the following expression, x times y over k. Okay, so it's nice to think, though, is when we're looking at double sums, it's a lot like with double integrals, is that you can handle these things one at a time. So I like to sometimes put brackets around the inside sum to indicate that for each value of x corresponds to a sum with the value y. So if we can figure out how to simplify this inner sum, we can then simplify the outer sum, and that makes computation easier. So what is this equal to? Well, if we notice here is that for this index, in the first sum here, x doesn't change as y does. So y is the index of the first sum. So x and k can be pulled out. Oops. Looks like the following. But we can go one further here, is that 1 over k can also be pulled out of this outer sum because it's a constant. But notice also is that this entire sum here is independent of x. So this entire sum, which is a number, can also be pulled out of the outer sum. So what does this result in? Just as follows. So these two sums are the same. So if we can solve one, we have the other. I'm going to use the one formula. So this is a small sum. It's just y equals 1 to 3. But we can still use the formula here. This is sum of consecutive integers beginning at 1 and ending at 3. There's a formula for that. It will be 3 plus 1 times 3 divided by 2. And similarly, the second sum is also and when doing this sum out, or this product simplifies to 36 over k. And by definition, since this is a joint PMF, this double sum must equate to 1. So therefore, k is equal to 36, and we now have it's x times y, going off the screen a little bit, x times y over 36 and 0 otherwise. So the same as before, but we can now substitute k out for 36. Part B. What are the marginal PMFs of x and y now? Well, by definition, or by conclusion, we really derive this, that the marginal PMF of capital X is just the sum over all possible y values, little p of x comma y. So in this case, the possible y values in which our joint PMF is non-zero So the values little y is equal to 1 to 3 of our PMF, which will be x times y divided by 36. So summing this up, again, y over 36 is constant, or I'm sorry, x over 36 is constant, so it can be pulled out of the sum. And as was seen last time, the sum is just equal to 6. We're using the formula that was used. This will be 3 plus 1 divided by 2, which all simplifies to x over 6. So two things need to be said. Is that one, is that after doing this summation, so even though when we started out, it looks like this is an expression of x and y, it's not. It's only an expression of x because y is the index in this sum. And so after carrying out our procedure, we end up with x over 6. Also, this is not quite true for all values of x. This is only true in which x is also between 1 and 3. So therefore, our marginal PMF is also piecewise defined. It's x over 6, given that x falls between 1 and 3. And is 0 otherwise. Similarly, looks like the following. But we can use a really nice fact about this particular PMF to save ourselves time, or this joint PMF, is that it's symmetric. In other words, we can switch the x and the y and it's still the same. And you can check that with the definition. So you can see that x times y over 36, that's commutative. That's the same as y times x over 36. So therefore, looks just like so. So what's the significance about this is that we've already calculated this expression above. The only difference is that now the roles of x and y have switched. So we're doing the exact same thing, but calling what's x y and what's y x. So therefore, this must also simplify to y over 6 under the restriction that y is in between 1 and 3. Therefore, the joint PMF of y, the marginal PMF for y is simply y over 6 for y between 1 and 3, and given that y is an integer, and 0 otherwise. So that concludes this video. In the next video, we'll be talking about continuous random variables and the analogous structures that we've talked about here.